Okay, welcome to chemistry here. We're going to talk about pH calculations today. And the first thing though that we have to talk about is what molar means. And molar, often represented with just a large M here, means moles per liter of solution. Okay, so what that means is if I have 1 molar HCl solution, that means I have 1 liter of water and I have 1 mole of HCl in that liter of solution. Okay, if I would have 2 liters of water, then that means I would have 2 moles of HCl. Okay, it's pretty basic. Just make sure you understand. If I had a 3 molar HCl solution and I had 1.5 liters of solution, that would mean I would have 4.5 moles of HCl in solution. So we'll be using this abbreviation quite a bit, and that means moles per liter. So to continue our discussion about pH and pH calculations here, the first thing we have to talk about is dissociation. Okay, so dissociation is a word commonly used here in acids and bases. And what that means is the particle splits apart. So if I have HCl, the dissociation will give me an H plus and a Cl negative. If I have, H2SO4, the complete dissociation of this would give me an H plus, another H plus, and an SO4. So that's what the word dissociation means when we use it. This is what we'll be talking about. Another kind of term for the same action is called ionization. As you can see, there are ions being formed during this dissociation process. So this is either called dissociation or ionization. One thing very interesting about water is it has what we call self-ionization. And that self-ionization occurs constantly. So we have a thing of water here. We know there's HOH pieces in here. But there's a self-ionization that occurs. And it splits up into an H positive, OH negative. And at all times we have particles of these H positives and OH negative ions. Now just so you know, when we talk about acids, we can call this ion a proton. We can call it a hydrogen ion. We can call it, so proton is one name for this. Hydrogen ion is another. And then the hydronium ion is really another form of this, because what happens in water is this gets attached to an H2O particle, making this H3O particle, which is called the hydronium ion. All three of these names will really mean the same thing for this chapter. So this action happens in water constantly, and we have this thing called the ion product constant for water. Okay? And the ion product constant for water is this. It's 1 times 10 to the negative 14th. And that equals all of the H pluses multiplied by all of the OH negatives. Now if you think about what we talked about here, if we split this into an H plus and an OH negative, you can see that for every 1 proton we get, we're going to get a hydroxide ion. So the number of protons or hydronium ions is always equal to the hydroxide ions if the molecule they're coming from is water. There's no other way to split water into ion form. So this ends up being the same number. So in plain water, or pure H2O, what we get is 1 times 10 to the negative 7th protons, and 1 times 10 to the negative 7th hydroxide ions. And we can see that these are the same numbers. And if you multiply these numbers together, you can see that you'll come up with this constant. And you can think of this constant as kind of, all that water can hold as far as ion. Okay, so that brings us to the discussion about what's different with an acid in water. So one thing that we need to define is a strong acid, and that is one that completely dissociates. So HCl is a strong acid, and what that means is if I put 100 pieces of HCl in water, then I'll get 100 protons, and I'll get 100 negative chlorine ions. That's what a strong acid is. It goes through complete dissociation. And then on the other hand, if I have a weak acid, then that'll be just partial dissociation. So like, this is a weak acid. If I have 100 pieces of this weak acid, I might only get, 1 or 2 pieces of protons, and then 1 or 2 pieces of the fluorine ion. And so that's the difference between a weak and a strong acid. So we're going to talk today about how to figure out the pH of strong acids. So this is what happens when I put a strong acid in water. If I put HCl in water, then I get these protons floating around, and they're taking up space because remember we had that ion product constant, which is 1 times 10 to the negative 14. So if I'm getting protons here out of this hydrochloric acid, then it's taking the space of the pieces that could be split from the water. Like, so if I split a water, I get a proton and an OH every time. But you can see when I split this, I don't get an OH. All I get are these protons. And so that's why it changes my numbers. Because before, I had, in plain water, my concentration was 1 times 10 to the negative 7 of both protons and hydroxide ions. But now you can see I'm clearly going to have more protons because they're coming from the hydrochloric acid. So, if I would happen to put hydrochloric acid into this cup, and I found out that I had a proton concentration of 1 times 10 to the negative 5th, I want to figure out what my hydroxide concentration is. Well, 1 times 10 to the negative 14th is the constant. That equals the protons multiplied by the hydroxide ions. And so in this case, I have 1 times 10 to the negative 5th, which cancels out, to divide this side by 1 times 10 to the negative 5th. And I find out that my hydroxide ion concentration then is 1 times 10 to the negative 9th. Now, kind of a common misconception here is that, hey, if this number gets bigger, that means this number gets bigger. But the reason why this is a bigger number is because it's negative. And it's negative 5 versus negative 9. So this one is a smaller number. And so I can see that my hydroxide concentration is 1 times 10 to the negative 9th in this situation. Now, so finally we can talk about our pH. And pH is index of hydrogen ions. So pH equals the negative log of the hydrogen ion concentration. So in this case, our pH is equal to the negative log of 1 times 10 to the negative 5th. And we can see that our pH then is going to be a 5. Okay? Now a pOH, like pH, is an index for the hydroxide ion concentration. And pOH is equal to the negative log of the hydroxide ions. So in this case, the pOH of this is the negative log of 1 times 10 to the negative 9th. And we can see then our pOH is equal to 9. Now if you look at these two numbers here, and we add those two up, we can see that pH plus pOH equals 14. And in this case we have 5 plus 9 equals 14. And that's always the case. So if you're able to find either your pOH or your pH, you'll be able to find the other because it's just the sum of the two equaling 14. So I'm getting the feeling that we should do one more. Okay. So we're going to start fresh here. And we're going to say we have water and we add into that water some HCl. And so we know that we're going to get this overabundance of protons versus the hydroxide ions. And by the time we're all done, we're going to find out that our hydroxide ion concentration is equal to 1.32 times 10 to the negative 10. Okay? And so I want to figure out what the pH is of this solution. But I also want to figure out what the concentration is of the hydroxides, or of the protons first. So I know that 1 times 10 to the negative 14th is my constant. And so if I divide both sides by 1.32 times 10 to the negative 16th, or times 10 to the negative 10th, sorry, 1.32 times 10 to the negative 10th, I will find out that my hydrogen concentration is 7.58 times 10 to the negative 5th. So that is my hydrogen ion concentration. And now I can use that to find my pH, because pH is equal to the negative log of the hydrogen ions. So in this case, the pH is equal to the negative log of the hydrogen ion concentration of 7.58 times 10 to the negative 5th. And in this case, the pH is equal to 4.121. Okay. And since my pH plus my pOH is equal to 14, then I can say my pOH is equal to 14 minus 4.121. My pOH is equal to 9.89. Okay? So, for today's assignment, I'll be asking you to make pH calculations, pOH calculations, and I'll also be asking you to solve for the different concentrations of the ions. Thanks. Have a good day.